We figured out from the density of Jupiter that it's probably not made out of rock. In fact, it's probably not even made out of ice, even though its density is higher than that of ice, but it would be compressed on the inside by so much that its density would be even higher. We suspected that, in fact, it's made out of gas. What gas? Well, we're going to start by just taking an educated guess and then work from there. An educated guess might be that Jupiter is made out of the same materials and the same amounts of materials that the sun is. The sun is approximately 75% hydrogen and 25% helium. Close enough. It's not exactly right, but it's worth exploring. What would Jupiter be like if it had this same composition? Can we explain the size of Jupiter, the density of Jupiter, and other properties that we'll talk about later by assuming a composition like this? The answer is going to turn out to be no. It'll be close to this, but there'll be some very important details that we figure out. But this will be a good start to help us on our way. Okay, so the first thing that we keep talking about is that inside of Jupiter, there's so much pressure from all the material on top of it that everything's going to be compressed so much and get higher density. So the first question we might ask ourselves is, how can we figure out what the pressures are inside of Jupiter? Here we're going to make an assumption, and that assumption is that Jupiter is in hydrostatic equilibrium. Let's look at that for a minute. Hydrostatic equilibrium. Hydro means liquid. Static means not moving. We're going to make the assumption that Jupiter, the interior of Jupiter, is a liquid that's not moving. And equilibrium in this case means that there's some sort of balance between something and something else. We'll figure out what that is in a minute. But what we're saying when we say that something is in hydrostatic equilibrium, we're saying that the support for Jupiter, the reason Jupiter doesn't collapse back on itself, is not because there's roiling motion inside there that's keeping everything supported, or huge temperatures that making everything boil. It's because Jupiter is simply behaving like a stationary fluid. Now, it seems crazy. I said that it's mostly hydrogen and helium. Why could we call it a fluid, hydrostatic? In fact, though, hydrostatic equilibrium is a pretty good assumption for all of the planets. Even the Earth, the interior of the Earth, is in something close to hydrostatic equilibrium, even though it's actually more like a solid than it is like a liquid. And we use hydrostatic equilibrium to discuss things like the Earth's atmosphere, which is again a gas and not a liquid. So when we say hydrostatic equilibrium, we can mean gases, we can mean liquids, we can even mean solids. And what we really mean is something very specific. And that is that the weight of all the stuff on top of you is balanced by the pressure of you. And by you, I mean a little parcel of, in the case of the Earth, a little parcel of air. In the case of Jupiter, a little parcel of Jupiter's interior. In the case of the Earth, a parcel of rock. If I look at, let's look at the Earth case. If I look at this little piece of air in my hands right this minute, well, this piece of air in my hands right this minute has a lot of air above it, which is pushing down on it. And the only reason it doesn't collapse on itself is because as it pushes down on it, my parcel of air also has pressure pushing it out, and those two things balance. They are in equilibrium. We can use that idea to figure out what the pressure is as a function of altitude in something like the Earth's atmosphere. Let's do it this way. What we'd like to figure out is the pressure as a function of height, let's say, above the Earth. Here's the surface of the Earth. Here's height going up, and we'd like to know what the pressure is as you go up above the surface of the Earth. P of Z, we'll call it. Well, we know the pressure at the surface of the Earth because we can measure it. You get out your barometer or something else and see what the pressure is. And we can actually figure out pretty easily what the pressure is just a little bit above the surface of the Earth. Let's say that we go up by 1 meter above the surface of the Earth. Not very much. We actually know that the pressure 1 meter above the surface of the Earth is about the same as the pressure at the surface. So, but let's say pressure at 0 is equal to, we'll call it P naught. Pressure at 1 meter, well, it's almost the same as the pressure down here at 0, but because it's all due to the weight of the air on top pushing down, but there's less weight. Why is there less weight? Because this little parcel of air is no longer sitting on top of us because we're up a little bit higher. So we subtract the pressure due to this little parcel of air. What is the pressure of that? Well, it's the density of this material, whatever that is. We have the pressure at 0 minus the pressure that would have been caused by this little bit of this 1 meter high slab. So that's equal to the density of the gas, rho, the gravitational pull of the gas, and now our 1 meter size. Let's make sure this makes sense. Pressure, as you remember, is a force per unit area, force per meter squared. The gravitational force of the Earth times mass would be equal to a force, but you have, instead of a mass, you have a density, which is mass divided by volume. We're multiplying that by the height here to get mass per unit area, so we have a force per unit area is minus rho g times 1 meter. What's the pressure at 2 meters? Well, the pressure at 2 meters is pressure at 1 meter minus rho g times 1 meter. We could do this forever. I think you see the pattern. And I'm going to write it down in a suggestive way. P of z plus delta z is equal to P of z minus rho g times delta z. Now I'm not just talking about 1 meter steps. I'm talking about any kind of small step that we could do. And I'm going to rewrite this in an even more suggestive way. And I'm going to then take you back to high school calculus and remind you that this thing that I just wrote down is the definition that you have seen before of the derivative. This is dp dz. The derivative of p with respect to z is equal to minus rho g. This is a differential equation, but it's about the simplest differential equation in the world. And in our simplest possible case, we can write the solution to this differential equation as P of z is equal to P naught minus rho g z. Let's make sure that this differential equation works. If I take dp dz, this is a constant, it goes away. dp dz is minus rho g. That's exactly what our differential equation was over here. It's okay if you haven't seen differential equations in 30 years or perhaps have never seen them. All this is saying is that the change in pressure as a function of height is proportional to rho times g. And all this is saying is that the pressure is a linear function of z in a very special case. The very special case is that rho and g are not functions of z. They do not change with height. In fact, this is only true if the density of the material does not change with compression. And this is true for an incompressible fluid. Now, we haven't been talking about incompressible fluid. We've been talking about how the high pressures inside of Jupiter cause the gas to get higher density, and that's certainly the case true. But there is a good example of an incompressible fluid or a nearly incompressible fluid where this equation works very well, and that's water. Water, as you know, if you take a piston full of water and you try to compress that water, it's really hard to do. Water is, at typical pressures, nearly incompressible. So what does that mean? That means that if you have water on top of you, that the pressure that you feel from that water increases constantly as a function of z, the distance that you have, the amount of water that you have on top of you. If you've ever done scuba diving, you actually know this already. You know that at the surface, before you go underwater, there is 1 atmosphere of pressure. You know that something like 10 meters down, there are 2 atmospheres. You know that something like 20 meters down, there are 3 atmospheres, and it keeps on going. Every 10 meters, you get another atmosphere on top of you. That's purely because water is nearly incompressible, and it follows this equation right here. Even if they were made out of water, there's so much pressure that water would break down and become higher density too. And the gases that they're actually made out of are certainly quite compressible. So we have to think a little bit harder about how we're going to use this equation to figure out Jupiter. So there are, of course, 2 complications here. One is that this is the force of gravity, and the force of gravity changes as you go up in, say, the Earth's atmosphere. The gravity gets less the higher you are. We are going to completely ignore that one right now because it's just an extra mathematical complication that we at least understand and we could figure out how to deal with, but we're not going to. The other interesting thing, of course, is that the density changes as a function of height, but really what the density changes as is a function of pressure. The higher the pressure, the higher the density. So really, rho is a function of P. And now, if you know your differential equations, you realize this is no longer a simple differential equation because this is a function of P and this is a function of P. And there is no general solution to this equation unless we know what this function is right here, rho as a function of P. Rho as a function of P, rho of course is the density, is generically called an equation of state. And figuring out the equation of state, figuring out what the density of material is as a function of pressure, is a critically important experimental and theoretical task for trying to understand the interiors of things like giant planets All of us know a really simple equation of state, though, and without even realizing that that's what it was. You probably learned in high school, my favorite equation of state, the ideal gas law. And if you learned it like I did, you learned that PV equals nRT. This is the pressure. This is the volume of the gas in a balloon or in a piston or something. N is the number of moles of material, which is just a measure of the amount of that gas inside of the thing. R is the ideal gas constant, universal gas constant, and T is the temperature. Temperature we haven't talked about before. Now you don't see density here anywhere, but you can take this and say P equals N over V RT, and N over V, the amount of material per volume. Not surprisingly, that's actually a density. Pressure equals density, and to get the units right, you have to divide by mu, the mean molecular mass. So something like hydrogen has a very low molecular mass. If it's just H2, it's really just 2 protons. Something like oxygen is much higher, but we don't need to worry about that too much right now. We're just going to write it as this and know that we now have an equation for density as a function of pressure. We have an equation of state. Now you may say, this is great. We can now go figure out everything about the interior of Jupiter, and you would be wrong, because the ideal gas law is only good for ideal gases. Ideal gases are things that are something like the pressure of the Earth's atmosphere is a pretty nice ideal gas. As you compress gases more and more, their equation of state gets further and further away from the ideal gas law. But it will be good enough for us to at least get a feel for how this is going. I'm going to now solve this equation for density and say density is pressure times mu divided by RT, and I'm going to substitute up in here and get that dP dz is minus G times P mu over RT. This is great because although it's a little bit more complicated than the differential equation we had before, it's a really simple differential equation. If you remember, again, anything about your derivatives or differential equations, you might remember that d dx of e to the x equals e to the x. It's one of the nicest things to differentiate in the world. And if we had d dx of a times e to the x, it's equal to a times e to the ax. And if you look at this, we have dp dz is proportional to p. And so we can simply write that p of z is equal to some constant, which will be the pressure at the surface of the Earth, times e to the minus g mu over RT times Z. And even if you don't think much about what this stuff is here, you find that the pressure as you go up decreases exponentially with altitude. So if I plotted pressure versus altitude, I'm going to do pressure here, altitude this way. It starts out at P naught and it decreases exponentially as it goes up. This is still not quite good enough because we made one more assumption, which is that T is a constant. And in fact, T is not a constant. The temperature changes greatly, as you know, as you go up in the Earth's atmosphere, you cool down. And so we actually needed to, back here, have T as a function of Z2. And then it gets really super complicated. But you get the general idea that you can use this equation of hydrostatic equilibrium, this one right here, even though it gets complicated and complicated, as long as you have the equation of state of the material in question and you know the temperature dependence inside, you can use these things to figure out what the pressure is as a function of altitude. If you know the pressure as a function of altitude, you know the density as a function of altitude. And what you really want to do in this case is try to figure out, can we make the density of Jupiter match the measurement? You take the density that you derive at the center, add up all the densities as you get to the top, take the average density over the whole planet and say, did I get the right number? And we'll try that process, but first we have to do two things. We have to think a little bit harder about an equation of state for a hydrogen and a helium interior, and we have to deal seriously with this temperature variation. If we don't know the temperature, we have no idea what the interior of the planet is really like.